All right, good afternoon, good morning, good evening, good night, depending on when you're watching this video. So we are going to work through exercise number 3 from lecture set number 7. In this exercise, we have suppose the mean shell length of 583 randomly selected specimens of a sea snail species is 13.25 millimeters. Assuming sigma equals 3.12 millimeters, compute and interpret the margin of error for a 90% CI. All right, so the process here is going to be pretty similar to what we have seen so far. So for the margin of error, we can start with an assumption check as well. It's a good way to check to see which of the two margins of error we should be using, the standard normal based margin of error or the student t based margin of error. Okay, so simple random sample. We are told in the question that we have randomly selected specimen. If we're told that the specimen are randomly selected or the units are randomly selected, we can assume that SRS is valid. Okay, part 2, we can say X bar is normal. All right, in this case, we are told that we have 583 sea snails. So we can check this off and say, by the central limit theorem, since n is greater than 30. And then the last part is sigma known, which in A is true. We're told sigma is 3.12. Okay, now for the 90% margin of error, on step 1, we have alpha equals 1 minus 0.9, which is 0.10. Okay, so we need Z alpha over 2, which is Z 0.1 over 2, which is Z 0.05. Okay, so to find the Z score, we can use our student T table instead of the standard normal table. If we go to the end of our student T table, so this is page 2 at the very bottom, you'll notice that Z 0.05 is actually given to us directly, which is 1.645. So it saves us a bit of time from having to use the standard normal table and gives us the same value that we would find from that table. So this is 1.645. And then on step 2, we're going to have E is Z alpha over 2 multiplied by sigma over the square root of n. So this is 1.645 multiplied by 3.12 divided by the square root of 583, which is 0.21. All right. Okay, so then on step 3, we can say we are 90% confident that the error made in estimating mu using X bar is within 0.213 millimeters. Okay, so the margin of error is basically just telling us how, well, it's essentially telling us how wide the interval is going to be, but it represents the expected error that surrounds our point estimate X bar when using it to estimate the population mean. Okay, part B is actually a continuation of part A. It gives the same information and just says basically compute the interval. So the starting points for this are going to be exactly the same. And for the sake of completeness, we can just take the steps as they are written here, and we can translate them over just so that we have a complete solution sketch written out. But all of these things were verified in part A, so it's the same process. And now here we're going to have X bar plus or minus Z alpha over 2 multiplied by sigma over the square root of n, right? So this is going to be 13.25 plus or minus 0.213. Right. Okay. And then the result is 13.037 to 13.463. That's right. And then on the third step, we would just say we are 90% confident that the population mean shell length is between 13.037 and 13.463 millimeters. I should say mean shell length for this sea snail specimen. We should be very specific about the population we're working with. Okay, part C. Does the interval in B give evidence that the average shell length for this specimen is less than 13 millimeters? Okay, so the interval from B is 13.037 to 13.463. Okay, so what we can say here is since the lower bound is greater than 13 millimeters, the interval gives evidence that shell length is greater than 13 millimeters. Therefore, it does not give evidence that shell length is less than 13 millimeters. So we've seen a similar type of problem before, but essentially what the interval is telling us is where we believe the population mean lies. So in this case, it's telling us that we believe the population mean, or we're confident that the population mean is between 13.037 and 13.463. These values are strictly greater than 13. So therefore, the interval is actually giving us as evidence of the opposite effect, or the opposite situation, which is that this shell length is bigger than 13. So it's not giving evidence that it's less than 13. Okay, D, determine the sample size required to have a margin of error of 1 millimeter at the 90% level. So here we want to find N given E is equal to 1. So we have N is Z alpha over 2 times sigma divided by E all squared. Okay, so this is still a 90% interval, right? It says determine sample size for a 90% interval. Okay, so this is going to be times 3.12 and divided by 1 squared. All right, so we have 26.34135. So therefore, use n equals 27. Okay, in part E, it says, assuming sigma equals 3.12, find the 90% CI using the sample size from D if X bar is 12.75. All right, so this is basically the exact same problem that we saw in part B, except that we are now doing it with a new sample size. Okay, so in terms of assumptions, nothing is going to change from what we checked off earlier. I think we're still computing a 90% CI. So actually, these first two sets of checks, or the set of assumption checking and the calculation of the Z-score here, are going to be exactly the same in part E. The only thing that's changing for us is the step 2 values. So we're going to have X bar plus or minus Z alpha over 2 times sigma divided by the square root of n. Okay, so this is going to be 12.75 plus or minus 1.645 multiplied by 3.12 divided by the square root of 27. Okay. So this is going to give us 12.75 plus or minus 0.987, 0.988. Okay, and that means that our interval is going to be 11.762 to 13.738. Right. And then we would actually be able to borrow. So we're going to have the same interpretation that we had here, except that the values of the two bounds are now going to change because of the change in sample size. So we would just have this portion here. Oh, too big. So this is going to be 11.762 and 13.738. All right. And then in part F, it says, repeat the calculation, but assume S is 2.5. So in part F, we're saying, okay, imagine that you no longer have sigma. So if we were to take this initial assumption check from up here, oh no. I got way too far ahead of myself there. Right, so looking back on it now, you can see here I have by CLT because n is greater than 30 in part E, but the sample size is now only 27, so that's actually not true anymore, and I just skipped ahead. Sorry about that. All right, so this is a good learning lesson though, because how do we handle this situation? So, all right. Okay, so what's going to happen here is this is no longer going to be true. Okay. Right. So we don't know anything about the population. Our sample size isn't big enough for the central limit term to take over. It just misses it. So none of this is true anymore. Okay. So what happens is that this conclusion, now in terms of the work, and this is an interesting discussion because in terms of the work, The process is exactly the same. And what this highlights is that you can always plug things into software, or you can always plug values into the formula. And if you do that, you're still going to get a result out. But in this case, we can't actually verify normality. So when we write our conclusion, there has to be a caveat. So what we have to say is, if the normality assumption can be verified, then we are 90% confident. So our conclusion has to change to account for the fact that we don't know if we can assume that X bar is normal, right? Okay, so then in part F, it's going to be the same set of assumption checks, right? So we're going to have right, so this is still true. This is no longer true. And this is no longer true. Okay. We still want a 90% CI. Okay. So now we have 90% CI. Alpha is still 1 minus 0.9, which is 0.10. Okay. So we need T alpha over 2 n minus 1 now, or T alpha over 2 df, which is T 0.10 over 2 n minus 1, which is T 0.05 comma 26 in this case, because we're using the sample size from D. Okay. So now we go to our student T table. We're going to match 0.05 to 26, and that gives us 1.706. Okay. So our T value here is 1.706. Right. So then on step 2, we're going to have X bar plus or minus T alpha over 2, comma df multiplied by S over the square root of n. So this is going to be 12.75 plus or minus 1.706 multiplied by 2.5 divided by the square root of 27. .821. Right. So that's 11.929 to 13.571. All right, and then again, we're going to have the exact same conclusion we had above. The fact that it's a T interval versus a normal interval doesn't change the conclusion. And in this case, we still don't have that normality for X bar, so we still have this caveat here. But what does change in this case are simply the bounds that we measure in between. Okay, so as always, if you have any questions, let me know.